Colleagues, thank you so much for this invitation. Now, the Council on Higher Education has done a great deal of work over the past 2 decades in supporting student learning. The review of the extended degree curriculum programs almost a decade ago saw a key publication proposing an alternative approach to enabling access and success. Now, the reason for the proposal was that a significant number of our students drop out and take far longer than the minimum time to complete their qualifications. Now, one of the points of the report was to argue for an alternative approach to both the foundation funding model and the need for scaffolding support. Now, the report captured 4 essential curriculum principles, and what I'm going to do today is demonstrate how we can address these principles in our education programs by adopting a cumulative learning approach and using the affordances of technology so that we have a better chance of equipping our graduates for the complexities of the world of work and beyond. Now, I'm going to demonstrate this approach by drawing on the Scholarship of Teaching and Learning in the context of a particular departmental case study. Now, the 4 fundamental curriculum principles are foundation provision. At the entry level, there's a recognition that serious knowledge gaps need to be filled given problematic curricular assumptions about students' prior knowledge. Epistemic transitions. There's a need to explicitly scaffold students' epistemic development beyond foundation provision. There is the necessity for curriculum enrichment through a range of key literacies. And finally, there's the need to enable greater breadth of exposure in order to produce graduates for the contemporary world. Now, a major structural weakness in many of our engineering programs is that we often separate those 4 principles. We outsource the foundation, we treat the literacies generically, we allocate different exit level outcomes in terms of the different epistemic areas or the knowledge areas, which we are now problematically referring to as graduate attributes, but that's a conversation for another day. What we know from a wealth of local, national, and international literature and empirical studies is that embedding the foundational elements, literacies, and world of work practices in our curricula in a coherent, orchestrated manner leads to better equipped engineering graduates and improved employability prospects in engineering sectors, which we so desperately need if we are even to begin to address the significant sustainable development goal challenges we have on this continent and beyond. So, what does this embedded or coherent, orchestrated curriculum approach look like in practice? For that, we need to go to the Scholarship of Teaching and Learning for a moment, or more accurately, the sociology of education. If our job in engineering education is to enable students to connect the dots between why, what, and how in the context of who, when, where, and what if, then what we are doing is enabling students to make the connections between principles and procedures, between theory and practice. And when we do this, we're doing this in a cumulative manner. This wave that you're seeing over there is called the semantic wave. And it can help us to see how to enable cumulative learning. Now let's just look at this again. Here are the 4 curriculum principles in relation to an idealized cumulative wave in engineering over time. Now, the y-axis differentiates between abstract conceptual work, imagine it as being sort of up in the air, and concrete contextual work on the ground, real people, for example. Now, our biggest challenge is precisely this middle area, labeled application. This looks very different at different stages of the curriculum in different subject areas. Let's just take a look at the challenges of enabling cumulative learning through application at the key transition points in many of our engineering curricula. Now, these transition points are in many cases the classic so-called bottlenecks in our programs, the fundamental engineering sciences. Thermos, fluids, strength, structure, variations of concepts around electromagnetism. We see high failure, high repeater rates, and high dropout rates at this point nationally. Now, a major challenge for engineering education is understanding why this is the case. Is it the grasp of a particular natural science concept? Is it the use of mathematics? Is it the relationship between these two disciplinary areas in a particular context? Now, our second key bottleneck area from the national data is broadly the design space. Now, here we have added kinds of technologies and a specific application, such as an idealized or real-world problem. And this is made all the more complex because it relies on the cumulative grasp of everything you've seen before it: the natural, the mathematical, the engineering and technological sciences. And quite possibly, it's made even more complex because it's in relation to real people, resources and time constraints. Now, many of our students actually get to this point in their curriculum with gaps all along the way. So by this stage, engineering academics often don't know what the problem is. Now, we have learnt a few lessons during the past 2 years that actually help us to see more clearly what some of the problems are in addressing these epistemic transitions. A national study revealed that the assumption of digital fluency has been the greatest threat to equity of access and success in South Africa. Now, digital fluency, which is about technology, requires a very different kind of thinking to the more linear ways in which we teach the natural and mathematical sciences. Let's just unpack this for a moment. Now, this is a radical simplification, and I'm not going to dwell on it. But the kind of thinking to grasp natural science phenomena is quite linear in a hierarchical way. All the base concepts must be in place to move upward. Mathematics has multiple languages, each with their own rules, and you could apply different kinds of maths to the same problem. We often make our lives much easier and teach one way, one answer, one method approaches here. And this comes back to bite us really often. Now, when you add a technology to this combination of science and maths, it's a different ballgame entirely. The technology may have been constructed using the principles of science and maths, but we're not asking our students to create the technology itself. We're asking them to use it for a specific purpose. That technology then becomes just like any other language. And there are a myriad of types of hardware, software, tools, all with their own rules, which can change overnight and which require a different kind of decision-making logic. So what I've tried to represent in these graphics here are what might be happening in the brain in terms of when we learn and acquire these things. And you can see that in the logic-based space, we're talking about a really different ballgame in terms of complexity. Now, how do we get our students from the fundamental natural sciences through the mathematics, which they continue to use, into this logic-based space in the context of the complexity of a real-world problem? I'm going to take you on a cumulative learning journey in my context. And for that, we need to go back to our curriculum principles. So, a group of new lecturers all started at Stellenbosch in around 2015 and 2016. And I had the great fortune of taking them through our professional development program. And a number of them taught first years the very first core engineering, chemical engineering module. Chemistry 1 to 3.
In 2017, as a chemistry team, chemistry lecturing team, we decided to come up with a unit conversions competency test because we noticed certain gaps in our students. First of all, the ability to change between different unit systems and the ability to evaluate the meaning of numbers and the meaning of solutions after solving a problem. And these are things that we take for granted among students, and we expect our students to be able to do this, but we don't actually teach them how to do this. We set up the test to help students to go through a learning process, to practice how to do unit conversions. And we also wanted to instill in students a sense of how important unit conversions actually are. We're referring to, for example, a grasp of different concepts such as physics concepts or chemistry concepts. And what you can see here is some of the classifications. So principle of convention, significant figures, which is something that's also very important within our course. Some of the questions were plain arithmetic questions, which you didn't have to understand the context of the question, you just needed to understand the maths. And then some questions, especially on the estimation side, were questions that related to everyday things which students could understand. And we noticed that there were some questions in the question bank which students coming from certain contexts wouldn't be able to formulate a solution strategy for because they have no context of what the question is. So for example, if you ask a student to estimate the number of ping pong balls in a swimming pool, in an Olympic swimming pool, if a student doesn't know how big an Olympic sized swimming pool is, it becomes difficult to answer that particular question.
Okay, so what we did, it was a learning opportunity in chemical engineering 264, fluid mechanics for the second year chemical engineering group. Each student was asked to choose an application of fluid mechanics, whether that be in industry, in sport, nature medicine, etc. And then each student had to present in a video format, focusing on describing the application and the specific fluid mechanics fundamentals that are at work in the application chosen. Each video was simply a slideshow with a voice recording, and the video lengths were limited to 5 minutes. Each student could use software of their choice to create and edit the videos, although a Microsoft PowerPoint tutorial was provided. The videos were distributed among students within small groups of about 5, and each student's video was viewed and assessed by the 4 peers in their group, as well as one of the module instructors. One of the things that worked very well was giving the students the opportunity to choose their own topic or application. Initially, we asked the students to give 3 potential topics, and we chose the topic that they should focus on, so as to minimize duplicate topics later on when they were divided into groups. By giving the students a choice, we increased the buy-in from their side, because then they would be talking in their presentations about things that they were interested in. And we could also keep the scope or the fields open to allow them to choose any application from any area that they liked, instead of just the typical industry-related examples that they find in the textbooks. So the idea was to get them to start seeing the normal world around them through the eyes of fluid mechanics. And then in the small groups as well, we tried to vary the themes or the fields as much as possible so that each student could be exposed to applications from different contexts. So essentially asking the students themselves to find extra examples to supplement what they see in the textbooks.
Now, let's move into the third year. Process control. Here you can now see that we're wanting to link different kinds of concepts in application to the design of a plant-wide control system. The first stage, pulling mass and energy balances through into a real-world context, any kind of process plant really, is a little like that first year foundation exercise you saw. In other words, the concepts and the mathematics around translating those concepts. But now we have the complexity of a different set of abstract concepts that need to be included. Control principles. Control concepts and principles such as feedback, feed forward, single, multiple inputs and outputs. Now what we did in this subject was we identified the current levels of abstraction in the curriculum, 5 different levels of abstraction, all the way from the conservation of mass and energy principles through mathematical expressions of these, through block diagram schematics of process and control systems, into a simulation of a process and control system, down to the real world physical process and control system. We identified how they were being taught, and they were being taught in this kind of lecture-tut-prac sequence for the first 10 weeks, and they culminated in a 3-week plant-wide control system design project, and this was problematic. Now my colleague Lydia Orette, who was teaching this at the time, identified that a specific problem was moving from the block diagram schematic into the actual simulation. So she realized she had to scaffold the more complex knowledge type first. In other words, the use of the technology itself. So by introducing her MATLAB Simulink model of a plant-wide process control system first, she progressively links the application using the software back to the mass and energy concepts, to scaffolding slowly but surely the control concept she was trying to introduce. I just want to point out something right here now. You can see that trying to map the learning process on a 2D wave becomes a little too simplistic. Note how the assignments, those little purple shapes, all have different shapes. Now this was an early attempt to capture different levels of complexity across or over time. We'll get back to this in a moment. Quite simply, what Lydia did was the design project itself was broken into 5 assignments, with each new assignment representing increased complexity and a wider range of levels of abstraction over time. She used the assignments as the context for her lectures. Assignment 1, for example, involved the naive design and implementation of a simple feedback control loop controlling 1 output. By assignment 5, the complexity had increased, and we now began to address the design of feedback control for multiple outputs. Now, as you can see, each assignment focused on a specific topic area covered in actual lectures, but was located in practice within the control system as a whole. Now, a key finding in this whole exercise was the difficulty that students have in moving from the more theoretical block diagram, that level 3, that's below the diagonal as you can see, into the more practical simulation, what Lydia was calling level 4. Now the problem with the simulation environment is that a great deal is invisible. It is certainly more complex, and it follows the logic of any technology or software. Rapid changes, constant evolution. Just look at how many students struggle when they install the wrong version of the same software to be able to address the same problem. In other words, the principle of use when it comes to software is not the same as the principle behind a mass and energy equation. Now this L3, L4 gate represents one of our greatest challenges. Why does all of this matter? If you type the term technical skills into any browser, what you will get is a dire picture globally with profound implications for employability and progress. We have major challenges in existing technical, practical, and critical soft skills. Skills our graduates don't have and which employers desperately need. This problem is not new. We have been complaining about technical skills deficits for decades. Just look at these. We cannot teach all the technologies and applications industry wants, but we can teach our students how to think, how to adapt, how to work with others. Let's go back to the problem of enabling them to work with more complex technologies. Now, instead of our linear connecting of theory to practice, let's take a 3D view and we add a complexity axis. Okay? Now, this takes us to what we call the semantic plane. The idea is exactly the same as the wave, but now we are moving between theory and practice on the y-axis, or abstract concepts and concrete contexts, and we're taking complexity into account on the x-axis. By way of example, we go back to chemical engineering and see how they have integrated simple real-world elements there on the bottom left as a way to scaffold access to a complex pump and piping network. What my colleague Neo Motang was talking about earlier, the concept videos, is in fact a real-world practical that fluid students conduct as a way to anchor a few fundamental concepts through practical engagement. That was pre-COVID. She introduced the concept videos as a way to cope with the teaching in the online space, but to fulfill exactly the same principle. Here is a concept, link it to the real world, to something that you can see around you. Practically, you might even have engaged in it, okay, so that we can scaffold the knowledge building across different levels of complexity. So let's look at how we actually use this semantic plane. I'm going to go back to the problem of control systems. Now here we have exactly the same MATLAB Simulink issue observed in this case by my colleague Carl Kruger. Now, although this particular intervention is in the mechatronics program, he teaches control systems and Lydia Orett was responsible for process control. They're very, very similar elements. So in the mechatronics program, what Carl does is he has built a real, simple, concrete, Arduino-controlled ball-on-beam system to help students learn and implement control principles, navigating between what my colleague Lydia Orett mentioned as that L3, L4 gate. Let's just take a look at this practically. So, by analyzing what kind of learning is happening in relation to different levels of abstraction and complexity, he could design an iterative scaffolded trajectory over time using appropriate technologies. So he starts by anchoring the theoretical concept in the real world. So here is where you see the effects of forms of control. In this case, it was actually specifically state-space control. Okay, now you all do this in your teaching. I'm teaching you something, that's where it happens out in the world. But then what he does is he isolates, like Lydia Orett did, simple elements through this physical ball-on-beam system. I touch the ball on the beam, it rolls away from the point of balance, I hear the motor start up, and I observe the beam responding to correct the position of that ball. If I look at the Arduino code, there hidden behind it, for example, there are some parallels I can observe as I then move into a more complex model, the Simulink model. Now, as I start experimenting through scaffolded exercises in the model, I have access to another technology, a virtual animation in Simscape that shows me what's happening at the more abstract levels. Now, the output plot simultaneously is helping me with the calculation and the mathematical application elements. Now, the entire learning pathway is this constant iteration around and across this plane, carefully and coherently constructed, but it starts by the lecturer recognizing what kind of learning is possible with what kind of technology. Now, if we take this complexity, for example, back to the real world, I'll give you a different example. So here, going back to chemical engineering, we look at a fourth year subject that they have. In their final year, my colleague Professor Christy Dorflin integrated a week-long series of site visits to mining and metallurgy plants in Gauteng, so that those students' final year projects could more explicitly link theory to practice in a complex context. So building on this initial part of the wave, this initial lecture, tutorial, practical, semantic wave, the site visit then enables the student not only to link those concepts, and this understanding was revealed in improved assessment performance, but also to develop a better grasp of what happens in actual practice. Students commented on learning about the health and safety of chemical and engineering operations, about process economics, the scale of technologies, and the interesting relationships between different operators, technicians, engineers, managers in those spaces. What I've attempted to do is two things. One, I wanted to demonstrate how important it is to take a program-wide approach to the holistic development of engineering students. And secondly, how different kinds of technologies can be used to link theory to practice with increasing degrees of complexity. The different technologies can enrich digital and quantitative literacies, for example, as well as aid in those fundamental epistemic transitions. Now, making the links between theory and practice goes beyond what I've already said. Let's just talk about contextualization as enhancement, our fourth curriculum principle. We need to be making the connections between theory and practice, between simple and complex, across local, national, and global sites of practice. We need to draw on accessible, localized, and globalized theories, acknowledge what our students bring with them, rich access to different interpretations of concepts and contexts. But we cannot do it on our own. We cannot teach or even access all the technologies out there. We are not industry, but we have to equip our students for industry and the world out there. And we can start with a better and more informed understanding of how to do it. And sometimes tools such as those from the Scholarship of Teaching and Learning can actually help us to see what is happening so that we can design transformative learning experiences.